Today's topic is group theory. It's a branch of abstract algebra. It is built from two simple things. One is any set G, non-empty set G, and one binary operation. So, the topics in this module are binary operation, group definition, properties of groups, some particular groups, subgroups, cyclic group, Coset and Lagrange's theorem. Binary operation on any given set S is nothing but a rule which will take two elements from that set and combine them and produce a new element which will be again in the given set. Such an operation is called a binary operation. For example, if I take set here, a binary operation, in general we write it as star. Is it a binary or not? We will check. If I take set G as set of integers Z and the binary operation as addition operation. So when we say it is a binary operation, take any two integers from set Z, add them, and then again we are getting an integer itself which belongs to Z. So hence the binary operation addition is called the binary operation. Now for the same set Z, if I take minus, so subtraction of two integers is again an integer, so it is also a binary operation, hence it is a binary operation. Then take the binary operation star multiplication for the same set Z. Now whether this is a binary operation or not, so multiplication of two integer is again an integer, hence this is also a binary operation. If I take division and the set G as again Z, here division is not a binary operation because if you take two integers, say 3 and 5, and divide them, 3 by 5 is not an integer, it is a fraction, so that does not belong to Z. So division is not a binary operation on Z. Now instead of Z, if I take natural numbers, then the operation taken is say plus. Now is this plus is a binary operation or not? Take any two natural numbers, add them, again it will be a natural number, hence it is a binary operation. If you take minus, whether this forms a binary operation on the set of natural numbers. Take any two natural numbers and subtract them. Say for example, I take 7 is a natural number, 9 is another natural number. 7 minus 9 is minus 2. But minus 2 does not belong to the set of natural numbers. Hence, minus is not a binary operation on set of natural numbers. Next is closure property. So for every two elements A and B belonging to the set A, if A star B again belongs to A, then we say the set A is closed under the binary operation star. That is what we have seen here. Now we will define what is a group. So consider one non-empty set G, and one binary operation star on G. Then we say this structure is a group if it satisfies four conditions or axioms. First one is closure property. For all AB belonging to G, if A star B also belongs to G, then we say it is a closure property. Associative property. Take three elements A, B, C from G. then A star B, then star C. If it is equal to A star bracket B star C, then we say it is associative property. Next is identity element should exist in G. There should be an unique element E belonging to G such that for any given A star E should be equal to E star A, and that should be again A itself for every element A belonging to G. Then we say that as such an element E as a identity element. Inverse should exist. For every element A belonging to G, there should be an element which is called the inverse such that A star A inverse is equal to A inverse star A is equal to the identity element E. Then we say A inverse is inverse of the element A. So if these four axioms are satisfied, we say this forms a group denoted by G comma star. If only one property, closure property is satisfied, we say it as a groupoid. If two properties are satisfied, we say it is a semi-group. If first three properties are satisfied, we call it as monoid. If all the four properties are satisfied, it becomes a group. So in this module, we are studying about the groups only. So all these four axioms have to be satisfied. In addition to these four, if the commutative property is also true, then we say such group is an abelian group. So a group G star is said to be an abelian group if A star B is equal to B star A for all A and B belonging to G. So one example we take here. G be the set of integers Z and the binary operation star is taken as plus here. This forms an abelian group, but Z with binary operation minus will not form a group. So we'll prove the first one. If the binary operation is plus, it has to satisfy all the four properties. Closure property is true here because addition of two integers is again an integer for every two integers belonging to Z. Associative property also you can check. A plus B plus C is same as A plus of B plus C. Then how to find the identity element here? Take any element A belonging to Z, then A plus which element gives you back A only. Such an element is called an identity element. So the operation is plus here, so A plus 0 only will give A. So 0 is called the identity. 0 is the identity element. Now for every element belonging to Z, this is Z here, for every element belonging to Z there should exist its inverse. So inverse means A plus which element if you add, you are getting an identity element which is 0. So what should be this element? Now the binary operation is plus, hence A plus minus A gives you the identity element 0. So we say minus A is inverse of A. So hence the set of integers with the binary operation plus forms a group. These four axioms are true. Further we will check whether the commutative property is also true or not. A plus B is same as B plus A for every integer, hence it is an abelian group. Now we will check this Z with binary operation minus, whether it forms a group or not. If the binary operation is minus, then the closure property is true. Two integers, their difference is going to be again an integer. So closure property is true. Whether the associative property becomes true or not. Now bracket A minus B minus C is not equal to A minus bracket B minus C. For example, I have shown here A, B, C. I have taken 6, 5 and 1. So 6 minus 5 will be 1. Then 1 minus 1 becomes 0. And right side B minus C becomes 5 minus 1, that is 4. Then 6 minus 4 will be 2. So 0 is not equal to 2. Here the associative property is not satisfied. Hence it is not called a group. It is only groupoid. Show that set of all fourth roots of unity under the multiplication operation is an abelian group. So fourth roots of 1 are 1 minus 1, I minus I. So this forms one set G. In the operation, binary operation given is multiplication. So this is written in the form of a table. And in the first row, here we have written 1 minus 1, all the elements of G on the top row and in the column. Then multiplying 1 by 1, we get here 1 into minus 1. 1 minus 1 is minus 1, 1 into I is I, 1 into minus I is I, minus 1 into 1 is minus 1. So like this table is constructed. Now we will check whether the closure property is true or not, whether G is closed under the multiplication. So if you choose randomly any two numbers, two elements from G and multiply them, again it should be in this set. Then we say closure property is true. For example, all we cannot check here. I have just shown few of them. Minus I into 1 is minus I. That belongs to G. Minus I into I is minus I square. I square is minus 1. So minus minus becomes 1. But 1 is also an element of G. So like that you can check here. Multiplication of any two numbers here. Again a element of G. Next is associative property. Even that is true. You can check here. I, for example, I into minus 1 is minus I. Minus I into minus I will be plus I square. I square is minus 1. So minus 1 again belongs here. So similarly, right side you can check. Associative property is true. Now we will see which is the identity element for these four elements. So identity element is nothing but when you multiply any element of G with another element, you should get the same element. Then that number is called the identity. Here 1 is the identity element because 1 into 1 is 1. 1 into minus 1 is also minus 1. 1 into I gives you the I. 1 into minus I is minus I. So 1 is called the identity element. Next is inverse element. So how did we define the inverse here? A star A inverse should be the identity element. So star is here multiplication. So A into which element gives you 1. If A is 1, so 1 into 1 gives you 1. If A is minus 1 into minus 1 gives you identity element 1. If A is I into minus I is 1, minus I into I is 1. So inverse for every element exists. Inverse of 1 is 1, inverse of minus 1 is minus 1, and inverse of I is minus I, inverse of minus I is I. All those 4 axioms are satisfied. So this group G with multiplication as a binary operation forms a group. This is also a Abelian group because commutative property is also true. Take any 2 elements from G, multiply them, and also in a reverse way you get the same thing. There are certain important properties of groups. First one is, in every group there exists only one identity element. So identity element in a group is always unique. There will be only one identity element. Now to prove this, we prove it by contradiction method. So we assume there are 2 identity elements, E1 and E2. Then given any element A star E1 must be equal to E1 star A, that is equal to A. If E2 is also an identity element, then when you multiply A star E2 is equal to E2 star A, that is equal to A. So what we infer from 1 and 2 here, both of them are giving A. So it means what? A1 must be equal to E2. So both these are same. So there exists only one identity element. Next is, in any group every element has only one inverse. Even this property we can prove it by contradiction method. Let us take one element A. It should have unique inverse, but we assume here there are 2 inverse elements for A. Then by definition of inverse of A star A1 is equal to A1 star A is equal to E. That is first equation. Then if A2 is another inverse, then A star A2 will be equal to A2 star A is equal to identity element. So both are giving you the identity element. It means what? A1 must be equal to A2. So hence there will be only one inverse element for every element belonging to G. Or you can prove in another way. A1 can be written as A1 into E, because E is an identity element. Then A1 star, now E can be replaced by A star A2, because A2 is another inverse, E is nothing but A star A2. Now A and A2 are associated here. Now you can associate A1 and A. A1 into A1 star A is E, because A1 is considered as inverse. So A1 star A gives you E. E star A2 will be A2, because E is an identity element. So here left side is A1 and right side is A2. So A1 is equal to A2. There are 2 more properties. Third one, A inverse is A and AB inverse is B inverse star A inverse. Star I have not written, it is assumed here. AB means A star B. Let G be a set of non-zero real numbers, and let A star B is defined as A into B divided by 2. Okay. So whether it is an abelian group, we have to check. Closure property, in this order only we have to check. First closure, then associative, then identity, then inverse. Closure property, A and B are non-zero real numbers, so their multiplication is also non-zero. If you divide that by 2, that is again going to be a real number. So AB divided by 2 belongs to G. Next is associative property. A star B star C will be equal to this one. A star bracket B star C is equal to A star B star C. By definition it is B into C by 2. So A is one element, BC by 2 is another element. Again we are operating them using star. So this into this divided by 2. So 1 by 2 A into BC by 2. Then A star B, first we evaluate, that will be A by 2 by definition. Star C. So this is one element, multiply this by C and divide by 2. You will get 1 by 2 into ABC by 2. Both are same. So associative property is true for star. Identity element A star E must be equal to A. So what should be this E? E we have to find out. Now A star E, by definition it is A into E by 2. Right side is equal to A. Now if you cancel A, right side remains 1. So E is equal to 2 becomes the identity element. Inverse. Let A be any element in G and E be the identity element. E is 2 here. Then by definition of inverse, A star A inverse must be equal to identity element. Identity element is 2 in the previous step here if you see. And star is defined by A into A inverse by 2. So solve for A inverse. Taking to this side, it becomes A inverse equal to 4. Therefore, A inverse equal to 4 by A. So 4 by A is the inverse of A. So G with the binary operation star forms a group here. If it is commutative also, then we call it as abelian. It is naturally A star B is a normal multiplication. It is AB by 2. A into B we can write B into A by 2. That is nothing but B star A. So it is an abelian group. If dot is an operation on Z defined by x dot y is equal to x plus y plus 1, prove that the set Z with this binary operation forms an abelian group. So first what we have to check is closure property. X and y are integers, so x plus y is an integer, plus 1 is again an integer. So closure property is true. And similarly you can check here, associative property is also true. Next we will find what is an identity. X dot E must be equal to x. So what should be E here? So by definition of this binary operation, x and E are two elements. Their binary operation should give us x plus E plus 1 and right side is x. So solving for E, we find E equal to minus 1 is the identity. Next inverse. Let us take A inverse be the inverse of any element A. Then by definition A dot A inverse must be equal to E. E is minus 1 in this case, so right side is minus 1. Then by definition of this binary operation of these two elements, it will be A plus A inverse plus 1, that is equal to minus 1. So solving for A inverse, we get here minus times A plus 2 is the inverse for A. So this set, here the set is set is Z. So Z with binary operation dot forms a group. Also commutative property is true here. X dot y is same as y dot x. Y dot x. Therefore it is commutative also. Hence the group is Abelian group. It is an Abelian group. So I leave this for you to explore. Let G be a set of real numbers not equal to -1 and star be defined by A star B equal to A plus B plus AB. It is similar to the above one. Check for closure property, associative, identity and inverse. It is an Abelian group. Now there are certain particular groups based on their structure. They have been named. First one is Klein 4 group denoted by V4. 4 group means in that set there will be 4 elements. So those 4 elements are E, which is an identity. Then other 3 elements are A, B, C. So what is uniqueness about this Klein 4 group is E is identity. And there are 4 elements in this group. This is one property. E is the identity. Then every element is inverse of itself. These 4 properties are there. Every element is inverse of itself. Such a group is called the Klein group. It is given in this tabular form. So closure property, for example, is here the binary operation is multiplication. Star. A star B is C. C is again here. A star C is B. B is here. B star A is C. C is here. So you can check here the closure property is true and also associative property. Take any 3 elements from this set, then check the associative property, that is true. Then we will find what is an identity element here. For every element you can see X star becomes X itself. For example, A star A is E. So E is an identity element. Sorry, A star E is A. So when you do the binary operation of A with E, you are getting back A. So E is called the identity. Similarly, B star E is B. Hence E is the identity. C star E is again C itself. So we say E is an identity. Next is inverse. Every element is its own inverse. It is very clear from this table. A star A is E. So inverse of A is A. B star B is E. C star C is also E. It is commutative also. A star B is same as B star A. C star B is same as B star C and so on. So it is commutative. Hence this Klein 4 group is nothing but an Abelian group. There is one more special group which is called the additive group of integers modulo n. So what is uniqueness about this set is the set will be set of integers from 0 to n minus 1, that is Zn. For example, if n is 5, then the set contains 0, 1, 2, 3, 4. n minus 1 is 5 minus 1, that is 4. It will contain 5 elements if n is 5. Operation is addition modulo n. For example, n is 5 here. If n is 5, then z contains here 0, 1, 2, 5 minus 1, that is 4. Then 3 plus 4, for example, if you take any two elements from this, 3 plus 4 is 7. The operation here is addition modulo. So 7 mod 5 is 2, because when we write a mod n, it means what? It is the remainder. It is the remainder when a is divided by n. So 7 if you divide by 5, you will get the remainder as 2. And this 2 is again an element here in Z. Now closure property we will check. For every two integers x and y belonging to Z phi, x plus y mod n is an integer. It is always between 0 and n minus 1. Suppose n is the remainder will always be less than n minus 1. Hence, the remainder will be between 0 and n minus 1. For example, if I take n as 5, x as 2, y as 4, then 2 plus 4 is 6. Then 6 mod 5 will be 1, because when you divide 6 by 1, so by 5, you will get the remainder as 1. This is the remainder. So 1 belongs to Z phi. 1 belongs here. Associative property. Addition modulo n is associative. Identity element is 0. And the inverse will be n minus a mod n. Say if you fix n as 5, take any element from Z5, say for example 2, then 5 minus 2 mod n. 5 minus 2 is 3. 3 mod n is 3 itself. So 3 is inverse of 2. Inverse of 2 is 3. Commutative property is also true. Hence Zn plus is an abelian group. Similarly, there is one more, which is multiplicative group of integers. The operation is modulo n. A into B modulo n. Now next is subgroup. As the name itself suggests, so H is one subset of G. G is a group, and H also becomes a group under the same binary operation that is there in G. Then we say H is a subgroup of G. For example, Z plus we have checked, it is a group. So Z is G, here it is Z. Now you take a subgroup of G, which is H. In this case, call it as E, set of even integers. So there are even integers here, positive and negative. This forms a subgroup under the same binary operation plus. E is called the subgroup of Z. There is one theorem which helps in future. The statement is H is a subgroup of G if and only if for all AB belonging to H, AB inverse belongs to H. prove that intersection of two subgroups of a group is a subgroup of that given group. Let G be, the proof is like this. Let G be a group and H and K be subgroups of G here. So if A and B belong to intersection of H and K, it means what? A and B belong to both the sets H and K. So AB belongs to H, AB belongs to K. Now H and K are subgroups. So by the above theorem, AB inverse belongs to H as well as AB inverse belongs to K also. So this element AB inverse belongs to both H and K. It means what? AB inverse belongs to their intersection, H intersection K. So from the above theorem, H intersection K is a subgroup of G because AB inverse belongs there. Cyclic group. A group G is said to be cyclic if there exists an element G belonging to G such that every element of G is of the form G power n for some integer n. The element G is called the generator of group. So this definition will be clear when we see one particular example. Order of a group means it is a number of elements in the group, but order of an element is different. Order of group means number of elements in that group, in that set. But order of an element is, it is the smallest positive integer n such that G power n is equal to E. And that smallest positive integer n is called the order of G. So G is any element. So how many times you are multiplying that G in order to get the identity element. So that n becomes the order of that particular element. So W is a set consisting of the fourth roots of unity, 1 minus 1, I minus I. In W, the identity element is 1. We have checked this before. And we will see what is the order of 1. Order of 1 means how many times you have to multiply 1 with itself so that you will get 1. So only 1. That the order of 1 is 1. Now how many times you have to multiply minus 1 with itself so that you get the identity element 1. So minus 1 into minus 1 gives you 1. So order of minus 1 is 2. And order of I is 4 because I into I into I into I. I square is minus 1 and I square is minus 1. Minus 1 into minus 1 is 1. 1 is the identity. So 4 times we are multiplying, hence the order of I is 4. Similarly, order of minus 4 is also 1. Coset. G with binary operation star be a group and H with binary operation star be a subgroup of G. Then for any A belonging to G, the sets A star H, which is collection of all A star H, where small h comes from the set H, and this is called the left coset of H. Similarly, another set capital H star A is a collection of all the elements of the type H star A, where this small h is an element from the set H, and this is called right coset of H. So in the left coset, the elements of H set H are multiplied from left side. In the right coset, the elements of H are multiplied with A on the right side. Number of elements in these cosets will be same as the number of elements in H. That is order of coset, left coset or right coset. The order of cosets will be same as the order of H. That is number of elements, no change. Lagrange's theorem. If G is a finite group and H is a subgroup of G, then the order of H divides the order of G. So order of G means number of elements in G. It is also written as cardinality of G. Whenever H is a subgroup, then order of H divides the order of G, where H is a subgroup. Now to prove this, let us take G is a finite group, H is also finite because H is subset of G. The number of cosets of H in G is finite. So let us take HA1, HA2, HAN, HAR be the distinct right cosets of H in G. You can take left cosets also. Here we have taken right cosets. And they will be disjoint sets. When you take the union of them, you will get the set G. So that order of G will be order of individual cosets and their addition. So number of elements in this coset, number of elements in this coset all together gives you the number of elements in G. But order of coset HA1 will be same as order of coset HA2 and so on, and that is equal to order of the set H. I told you there is no change in the number of elements in the cosets and the set H. So it means what? Order of H order of H is equal to, we are adding the number of elements in H R number of times because there are R cosets. So R into order of H. In another way we can write cardinality of G is equal to R times cardinality of H. So what it implies is order of H divides the order of G because number of elements in G is R times number of elements in H. One example is here. Let G be a group with subgroups H and K. If order of G is 660, that is number of elements in G are 660 and number of elements in K is 66 and K is subset of H, H is in turn subset of G. What are the possible values for the number of elements in H? So to solve this we take the help of Lagrange's theorem. So H and K are subsets of G here. So order of H divides order of G. So 660 can be written as multiple of order of H. So we can write order of H into Q1 for some Q1 greater than 1. Next information is that order of K is 66. So 60 because K is subset of H, order of H will be 66 times some integer Q2 which is greater than 1. So next we want to find out here what is the order of H. So this you have to substitute here. So 660 is equal to order of H is replaced by 66 Q2, here Q1 is there. So 66 Q1 into Q2. So Q1, Q2 must be 10, then only it becomes 660. So the factors of 10 are 2 and 5. So one possibility is that Q1 is 2 but Q2 is 5. Another possibility is Q1 is 5 and Q2 is 2. So this completes this topic. If you find this video useful, like, subscribe and share, and thank you all for watching. Thank you.